Welcome to the class. Today we are going to discuss about the wave function of an infinite squirrel potential in one dimension. For this, let's take a particle which is confined in a box. Side has width A. If particle has mass m and it is constant to move in this box, but if we draw the energy diagram, here we can see that potential energy outside this box is equal to infinity, whereas inside the box it is 0. Simply we can write V equal to 0 or x is less than a and greater than 0 and infinite otherwise. So you can see we can divide it to region 1, region 2, region 3. To solve this, we have to write the Schrodinger equation in all three regions. For general Schrodinger equation, we can write here, which is d square psi by dx square plus 2m by s cross square e minus b psi equal to 0. One dimensional Schrodinger equation. From here you can see as at region for region 1 and 3 your potential energy goes to infinity, so that particle will not present in region 1 and 3. Their wave function must vanish. Then we are left with region 2. For region 2, our wave function becomes simply here we put v equal to 0 in Schrodinger equation, and that's become simply d square psi by dx square plus 2m e by s cross square psi equal to 0, and here we can define this as k square. So our equation become d square psi by dx square plus k square psi equal to 0 and k square equal to 2m e by s cross square. And general solution for this equation, psi is, we know it is a sin kx plus b cos kx. Now we have to put the boundary condition at these two boundaries, at x is equal to 0 and x is equal to a. We have two boundary where wave function vanishes at both boundary. We have to put the boundary condition. So boundary conditions. What are the boundary conditions? First one is psi of x at x is equal to 0 must vanish. Second one is psi of x at x is equal to a must vanish. From this boundary condition, we simply get b equal to 0. So we left with psi of x is equal to a sin kx. Now come to the second boundary condition. Here putting second boundary condition, we get k equal to n pi by a, and here wave function becomes now psi is equal to a sin n pi x by a, and n value goes 1 2 3 and like that, but 0 is not allowed. Why? Because wave function itself vanishes for n equal to 0. So we got psi as a sin n pi x by a, so we denote it as sin n. For different value of n, we will get the psi n. We can normalize this wave function to get value of a, which is equal to nothing but, after doing a simple integration, we will get a as 2 by a root over of 2 by a. So now we get the solution as that has to be psi equal to 2 by a root over, then sin n pi x by a. So this is your psi n, which is the required wave function. So this is the required wave function for one-dimensional infinite Squarewell potential. Thank you.